Okay, so we're going to try this out, see if I can show you what I'm talking about with these polar and nonpolar molecules. So first of all, let me show you, we'll compare water, H2O. Now, I'm not going to draw the Lewis structures for these. I'm going to kind of skip ahead, assuming that you can draw the Lewis structure and figure out how the atoms are going to be arranged for right now, and if not, we'll come back and do that. So anyway, in water, it turns out that we have oxygen, and then we have a couple of hydrogens, kind of like this. We've got a couple of lone pairs of electrons, which is why these hydrogens are arranged, kind of pushed down into this bent shape, like yay. And if you look at the bond between oxygen and hydrogen, we'll see that there's definitely a difference in the electronegativity between oxygen and hydrogen, so that the electrons get pulled in this direction. I'm drawing this as a dipole moment. It's not a very nicely drawn one, but get the idea. And that happens for both. Now, if you see the way that those are going to be pulled, that we're going to end up on this side of the molecule with the electrons being pulled towards the top. The way that I've drawn it, that's the top. And then they're pulled away from this side of the molecule. So you end up with a positive side of the molecule and a negative side of the molecule there on the bottom because of the bent shape. Now, just to show, let's just say that in a water molecule you didn't have that shape. Let's say that the water molecule ended up with this shape, so that the hydrogens were exactly opposite of each other. So the oxygen would still pull electrons this way, but you can see that for your sides of the molecule, here's a side and here's a side, you don't get any difference. There's no difference between what happens on the right side of the molecule and what happens on the left. There's no top or bottom in this case. Now if we look at ozone, ozone ends up giving you that kind of structure. So you can see it's got that same bent kind of structure, but because the bonds between the oxygens are not polar, since all the oxygens have the same electronegativity, there's no electrons are not pulled towards the top of that molecule like they were in the water. Now we could look at one more. I'm going to add a page here and we'll look at so let's say we were looking at another molecule. Let's look at, well, let's look at a couple. Let's look at ones that kind of have a similar formula. BF3. Now this is a special case. You probably could think of a better example than that in just a second. Versus NH3. And so when you look at BF3, and we've seen this before, you end up with a molecule that looks something like this. Now the special thing with the boron is it's happy with the 6 electrons instead of the 8. So even though fluorine is a lot more electronegative than the boron, you can see that the electrons would be pulled, I should be using a different color here, but in the direction of these arrows. But those fluorines are all going to try and pull the electrons to their side, so what you would end up with is something, I guess you might think it would look something like this. I'm showing just that the electrons would be pulled more to that side, but you can see that there's no difference between this side, and this side. That would be a planar molecule, and all 3 corners of that molecule would end up exactly the same. Now if I look at nitrogen or ammonia here, the shape that we end up with is different because it has a lone pair of electrons here. I'm not sure if I can draw this very well, but we have a hydrogen here, a hydrogen kind of here, and a hydrogen kind of here. So because that lone pair pushes all those bonded hydrogens kind of down. Now the difference in electronegativity between nitrogen and hydrogen is probably not that great, but nitrogen is probably a little bit more electronegative, and so you would have electrons being pulled like that towards the top of this molecule. The shape of this molecule would be a trigonal pyramidal molecule, but you would end up with, at the top, up where this nitrogen is, a slightly negative, and down here where all the hydrogens are would be slightly positive. And so this would be a more polar molecule, whereas the boron trifluoride, because of its shape being planar, all those poles end up kind of giving you the same at every side of the molecule.